Don't say anything to this guy. On va... Wait, why don't you have a mic?
For the people.
Ah, you're.
Yeah? Okay. So welcome everyone to the afternoon session. First speaker is Ignacio Manzur, and he will present all polynomial generators preserve distance with mutual correlated agreement.
Thank you, Anka, for the introduction. Okay, thank you, everyone. I'm very happy to be here. If you have any questions, just stop me. Okay, so if you went to a selected subset of talks yesterday, you already have like a lot of motivation for why we care about these things, but I'm just going to do a TLDR. So the way we build modern snarks is we build them from probabilistic proofs, and in turn, these objects are built from a mathematical object called linear code. Maybe you've seen this in Alice talk. And the property that you associate with these codes called distance preservation basically is the fundamental property that allows you to prove the security of these objects. And in particular, if you have good distance preservation, you have high soundness, high provable soundness, efficient snarks. So it's kind of like the takeaway. In fact, these questions are so important that maybe you've seen Dan's talk. Recently, there's been like $1 million associated with proving or disproving conjectures related to distance preservation and proximity gaps. So what is distance preservation? The point is that we have a linear code. This is an object that is a linear subspace, lives in Fn when F is a finite field. And I'm just going to consider like some word U1. It's at some distance of the code, and I'm going to visualize this by these red squares basically showing where it disagrees with the code. And then I have a bunch of these words. They are all at some distance of the code. And I want to test the proximity of these words to the code. I can do this by just testing each one of them, but this is like extremely inefficient. So now something that is completely omnipresent in the snark literature is that I'm going to use what we call a generator. This is a function that takes a set of seeds, maps it to a vector of field elements, and instead of testing each of them individually, I'm going to combine them with this generator. I'm going to obtain what I call the combined word. This is the word that is the linear combination where I take as coefficients the output entries of the generator vector. And basically, we want to preserve the information of distance. What we don't want to happen is that you have some word that is far from the code, but somehow magically when I combine it, like there's some cancellation happening, and then suddenly I'm like closer to the code. So distance preservation says the probability that the combined word is at distance less than the maximum distance of the original word is small. That's like a very basic kind of property. and fundamental when you're proving soundness. Kind of a fundamental foundational result in this line of work is RVW, and it tells you, okay, when you take like a random linear combination, meaning you choose the generator that just outputs the set of seeds, the probability that the maximum distance drops by a half is small. It's bound above by like 1 over the field size. This is not enough for applications like batch proximity testing. First of all, there's this distance drop. Like what is going on with like this half factor? And okay, there's like a line of work starting with AHIV and the Ligero protocol that kind of starts dealing with that distance drop. You can see also that there's only one generator that's considered. If you want to do like, I don't know, powers, then this tells you nothing about this. And there's like a bunch of works that want to use different things, powers, multivariate generators, all sorts of things. And you have no control over the agreement set. This result tells you nothing about where the combined word agrees with the code and what the relationship is with the agreement with respect to the agreement of the original words. There's no information about this. And so people have tried to like come up with like more granular notions of agreement, notably correlated agreement in BCIKS, and more recently in ACFY, mutual correlated agreement, which is a notion that we study in this paper, and is like kind of like the strongest notion of correlated agreement or distance preservation that we have. So what is mutual correlated agreement? Again, if you've seen some of the talks yesterday, you have like kind of a primer, but just want to give you like a picture that helps me think about it. So for simplicity, I'm just going to fix the generator to be random linear combinations of two words. Alpha 1, alpha 2 are going to be the coefficients. The goal is that except for a very small error over alpha 1 and alpha 2, the following picture happens. So I have U1 and U2. I take alpha 1 times U1. I sum alpha 2 plus U2, and I get this combined word, alpha 1 U1 plus alpha 2 U2. Now imagine that this kind of combined word agrees with a code word in the code over the set of positions that are kind of specified by the little arrows. Then it must be the case that both words U1 and U2 also agree with a code word over the same set of positions. Does that make sense? And here, like if you imagine like numbering from 1 to 8, the kind of little boxes, the common agreement set, which we call T, is like 1, 3, 7, 8, like the positions where they agree. Okay, so formally, I'm just going to like give you the definition once. We may go over it quickly, and then we'll kind of like move on from there. It's a bit of a mouthful. So we say that a generator has MCA error, epsilon MCA, which is a function from 0, 1 to itself, for some linear code C, if I give you like a list of words U1 to UL, and I give you a distance parameter gamma, then the probability that some event happens is bounded above by epsilon MCA at gamma. What is this event? Well, it's the existence of this set T, this common agreement set that we saw in the previous picture, but it has to be large. Like it has to be at least of size something controlled by gamma. And if basically you want the combination to agree, but some of the original word doesn't agree, some original word doesn't agree over the same set. This event is kind of like the opposite of what we saw in the other picture. We want this to not happen, so be bounded by epsilon MCA gamma. So just to give you like a little example of what happens when you start like plugging in values, for example, and we'll use this later. If you set the distance parameter to be 0, this simplifies to something a bit simpler. Basically, it says you take any set of words you want to UL, and then the probability that the combined word is in the code while some word was not in the code is small, bounded above by epsilon MCA at 0. So the epsilon, the error at 0 measures kind of is testing membership to the code. That's kind of the idea. Okay, we have this kind of new notion of MCA. What is it useful for? Maybe you've been to Nico's talk. It makes things nice in a lot of ways, but one of them is this. A key step in the security reduction of the snarks that are built from proximity testing is as follows. You have like a set of words you want to UL, and you're considering like the Hamming ball around it of some radius, let's say n gamma, which is basically the set of code words that are close simultaneously to all the UIs. And as I said, like you're combining it because you want to test something simpler, hopefully. So you're taking like the linear combination with the output entries of G, and you're asking yourself in this security reduction, actually what's like in the Hamming ball of the combined thing? And you can show that if you take like something in the Hamming ball of the original words, you do the same combination process, then you will be at the correct radius. Like this thing is in the Hamming ball. But what MCA allows you to conclude quite nicely is that actually, with very high probability, this is it. There's nothing else in there. Like list decoding and combining is the same thing as combining and list decoding. And that's like something that is very useful in security proofs, and we've seen in Nico's talk yesterday, very useful in simplifying existing analysis. And okay, you can do other stuff with it. You can do basically straight line extraction. You can prove round-by-round security, which is essential for kind of the non-interactive part of the SNARK part. Yeah. So what did we know about MCA? I think it was like basically the following landscape. We knew that for specific generators like lines or powers and RS codes, for example, you had MCA. And we knew that for line generators, for example, like just taking one word plus X times another, you had it for all linear codes. But above that, it was like basically, we didn't know what happened. So this leads to the very natural question, which generators have MCA? Can we characterize this? Can we like say something about like, is there structure there? So I think we kind of answer this question in a satisfactory way. The first thing we do is that we identify this condition called zero evading, which we prove is a necessary condition for MCA. So every MCA generator has to be zero evading first. And this gives you kind of like a sanity check for MCA, if you will, where, I don't know, like you're looking at this new thing, you don't know like what it does. At least like, if it's not zero evading, then there's no way that it's MCA. Then we show that every polynomial generator, meaning every generator whose output entries are polynomials in the inputs, has good MCA error. So this gives you like kind of a sufficient condition. On the other hand, where you can take like a very, very general, like a kind of random-looking generator, but if it's polynomial, you can show that it has good MCA. This error is tight in some regime, and I think we'll talk about it, but in the unique decoding radius, I think there's good information showing that it should scale linearly with distance. So we'll come back to this. But we also show that there exists polynomial generators which kind of don't fit this framework. So polynomials, generators that are not polynomials, but which have good MCA error, which shows that there's like kind of like something there that is still unexplored. And I think one nice thing that we get along the way is what we call the MCA toolbox, which is like kind of like a generic set of like propagation results that allows you to conclude MCA from the MCA for some generators by applying some transformations. Okay, so let's go over this. But first, like, okay, so what's the new landscape? The new landscape is we've shown that there's kind of like this hard barrier, like zero evading is necessary. We've shown that if you're polynomial, which includes like many of the examples that you see in the literature, then you have MCA, you have good MCA error. We've shown that there's something kind of like in between, and we have to figure out like what's going on there. And there's also like work in progress, generalizing this to maybe like polynomial generators over varieties and so on. So let's like kind of review this. So zero evading is necessary for MCA. So what is zero evading? When you have a generator, like you have a set of seeds, you send it to like a vector of field elements. For any like non-zero vector, you can consider the subset of seeds that send that vector to zero. Then zero evading kind of error is like an upper bound on the ratio of seeds that send the vector to zero and the set of seeds for every vector. So it's basically the maximum proportion of seeds that send any non-zero vector to zero. So how do you kind of go about showing this? I'm just going to like show a little proof sketch. The first thing we show, which is like kind of a by definition of MCA, is that it's monotonic in the distance. So in fact, it only suffices to show it at zero. And now, if you remember, like this little callback I was referring to, the epsilon, the MCA error at zero is testing membership to the code. So you show that if like the combined word is in the code, but some word was not in the code initially, then you can find some non-zero vector that is sent to zero. And the whole trick of the proof is to show that this choice is independent of the seed. So when you do this, like you show that the zero evading error like lower bounds the MCA error. What about the polynomial kind of result, the sufficient condition? Well, okay, as we said, the polynomial generator is like polynomial. The outputs are polynomials in the inputs. We also require that they're linearly independent over f to like avoid like some silly cancellations. So the result is that all polynomial generators have MCA for every linear code. So how do we kind of do this? The proof sketch is kind of simple. I mean, the devil is in the details, but you write the polynomial as like a sum of monomials. And this kind of expression shows that the generator in itself is like the combination of three things. There's like a big matrix that kind of tells you how to select monomials. And then there's like a big tensor product of univariate generators. The point is that this thing, the univariate powers, is a very simple building block you can analyze, and we do. And then it's just a matter of like propagating this to this entire thing. So what we show is that both tensoring and this linear transformation kind of preserves MCA or interacts nicely with MCA. And that's what we call the toolbox, which we'll see later. So let's just look at this result more like specifically. I mean, you can also specialize to RS codes and obtain MCA for all polynomial generators up to the Johnson bound. This is something you can do. But let's look at this like more quantitatively. So generator is polynomial. We call di the maximum degree in the variable xi. Then the MCA error looks a bit like this. So the delta c is the minimum distance of the code. But the important thing is that if you specialize like kind of this result to the univariate powers generator, then you see that for the distance parameter below delta c over d plus 2, the error is basically n gamma d over f. But what we do is like we have actually a matching lower bound. We show that there are codes such as when you're below their unique decoding radius, the MCA error is lower bounded by n gamma delta d over f. And I think this gives like pretty good indication that the error should be that. The error should be like basically n gamma d over f, and just should be linear in the distance parameter in the unique decoding radius. But I think it's a super interesting question to see if we can close the gap between delta. Yes?
About this, so the restriction on gamma being less than delta over d, is that inherent? That seems kind of...
No, I think it's an artifact of the proof. Yeah, and I think that's why it's interesting, and I think...
So that's what you're saying? Is that you're saying there about the... that's the point that you're asking about?
Yeah.
I see.
Yeah.
Okay.
Yeah. Thank you. Thank you for your question. Yeah. So what about this toolbox? I'm just going to show like some of the results. I think like there's more, but like just a little showcase. The first one that's mentioned in the previous result is the linear transformation. So you get a generator, you multiply it by some matrix. Okay, the matrix has to have like some property like a left inverse or something like this. But basically, we show that the MCA error is preserved exactly in this case. Similarly, like you take a tensor of two generators, just meaning you take like the tensor product of their output vectors, then we show that the MCA error is sum in that case. We have a very cute result showing that analyzing the MCA error of like the affine space generator is basically the same thing as analyzing the line. So you just need to understand the line up to some conversion factor, which is small, like at most 2. So really, like there's no kind of almost no loss, which gives basically the first bound for the affine space generator MCA error that doesn't depend on the number of variables. And then we have like this very interesting matrix vector product transformation, which allows us to show that a generator from the AGHP paper has good MCA error. And this is surprising because if you try to apply the polynomial result to that generator, you will get a trivial error because the degree... Sorry?
There are 3 generators there.
Which one? It's the one with like the... Okay, maybe I can show this. Yeah, it's fine. Like, I think it's a good question. It's this one. We call it the AGHP, but yeah, that's true that there's more than one. You basically have an isomorphism from FQ to the K to FQ to the K, and then like you take like kind of this product. Yeah. Okay, sorry, I have to go back to that. Yes. It's surprising because if you try to apply the polynomial result to that one, the isomorphism makes it have like such a large degree that the error you get is trivial. But in fact, like you can show that it does have good error, which shows that there's something else going on there. Okay, so now I want to quickly like go over like open problems, which I think are super exciting, and I wanted to share that with you. The first one is like, can we complete the characterization? So we've shown zero evading is sufficient. We've kind of like, you know, going like from the low end, like by showing that polynomial is sufficient, is necessary, or the other way around, polynomial is sufficient, and we get like more and more generators that seem to just have good MCA error. Can we show that, in fact, the zero evading property is sufficient and like be done with it? That's it. The other thing is like we chose, like we took this approach of like, you know, relying on structure by like considering this huge class of polynomial generators. A question is that necessary? Like, is structure necessary at all? You can argue with me now that uniformly random things are also structure because like they're like the absence of structure. Okay, but like basically take a random generator, meaning a uniformly random element of the set of functions from S to F to the L. You can show, and we don't do that, but you can, that with probability more than 1 over delta minus delta over that choice, the zero evading error will be bounded by some like error term. The question is like, can you follow up and show that it has MCA with good probability too? I don't know this, but I think it's super interesting. And like lastly, like just to keep in the theme like of the talks that we've seen, what can we do about like this distance parameter? So what we know today is if you specialize the result in the paper for basically degree 1 in each variable, meaning a multilinear generator, then you know that for arbitrary linear codes, we have good MCA up until like the 1.5 Johnson. This is because like the dependency is 1 over d plus 2. Then we know that for polynomial generators and Reed-Solomon codes, you can go up to the Johnson bound. And the question is like, can you say anything here? So this I also don't know. Otherwise, I would be rich. But yeah. Okay, so just to do a little recap, what we did is we took this MCA property and we asked like which generators have it. A fortiori, you have to be zero evading. That's something we show. If you're polynomial, then you're fine. And then there's like still a gap there that we have to kind of figure out. Okay, thanks a lot for your attention, and I'm happy to take your questions.
Any question?
Thank you for the talk. So yesterday in Dan's talk, he talked about line decodability and how that implies MCA. I'm guessing some kind of curve decodability implies other generators. How does line decodability relate to zero evading, and have you explored that area?
Yeah, it does. I mean, maybe I can show. No, maybe not this one. Okay, I don't have the result that I'm thinking about in the slides, but yes, it is related. In some sense, like there's a result that we have that actually I was very happy when I saw the line decodability because I think it kind of expresses that. But it's basically if you have too many points, and too many by that I mean like bigger than something that depends on the zero evading error, which have a certain property, then they're collinear. Like there's like a line going through that. So yeah, it's very much related. I mean, I can show you the. Yeah. Thank you.
Any other question? Okay, let's thank the speaker again.
Thank you.